All right, so have you ever just kind of looked up at the sky, on a clear day and been like, wait, why is it blue?
It's something we see all the time, but probably don't think about too much.
Yeah, exactly. And that's what we're diving into today. Like, what's the actual science behind why the sky looks blue?
It's actually way more fascinating than you might think.
For sure, not just like a simple answer. We found this really cool episode from the podcast, But Why? A podcast for curious kids that breaks it down.
Oh, yeah, I love that podcast.
And don't worry, even though it's aimed at kids, the science is totally legit.
Absolutely. It's great for all ages, really. We're going to be talking about light, the atmosphere, and even a bit about how our own eyes perceive color.
Okay, so, when I was a kid, I thought someone literally painted the sky blue.
Huh. I think a lot of kids think that.
But obviously that's not it. So where do we even begin with a real explanation?
Well, we got to start with sunlight.
Okay, so, we see sunlight as white, right?
Right, but here's the thing. Sunlight isn't actually white. It's made up of all the colors of the rainbow combined.
Whoa, wait, really?
Yeah, you know how you can see a rainbow after it rains or if you shine light through a prism? That's basically the white light getting separated into its individual colors.
Oh, right, like it's splitting it up or something.
Yeah, exactly. So all those colors are actually hidden within the white sunlight we see.
Huh. Okay, so then what happens to all those colors? How do we end up with just blue?
Well, that's where the atmosphere comes in.
Right, the atmosphere. It's filled with dust and water vapor and stuff, right?
Yep, all kinds of particles. And when sunlight hits those particles, it gets scattered. There's actually a name for it. It's called Rayleigh scattering.
Rayleigh scattering, okay.
Named after Lord Rayleigh, who is a physicist who figured all this out.
So wait, what does it mean for light to be scattered, though?
Imagine, throwing a bunch of marbles at a wall. They're going to bounce off in all different directions, right? That's kind of what's happening with the light. When it hits these particles in the atmosphere, it bounces off in all sorts of directions.
Oh, interesting. So it's not just like a straight beam of light going through.
No, it's getting all jumbled up. And here's the key. Different colors of light have different wavelengths.
Wavelengths, okay.
Yeah, you can think of them like waves in the ocean. Some are longer and more spread out, and some are shorter and closer together. Blue light has a really short wavelength.
Gotcha.
And guess what? Shorter wavelengths scatter more.
So blue light, with its short wavelength, is basically bouncing off those particles like crazy compared to the other colors.
Exactly. And because it's scattering so much, that blue light is what reaches our eyes from all directions, and that's why we see the sky as blue.
Whoa, okay. That's kind of mind-blowing. I always thought, the sky itself was blue, not that it was the light we were seeing.
It's a really common misconception.
Yeah.
But it shows how much our perception of the world depends on how light interacts with it.
That's wild. So, if there wasn't much stuff in the atmosphere, would we even see a blue sky?
That's a great question, and it brings us to our next point. You're absolutely right. If there were fewer particles, the sky wouldn't be as vibrant.
Huh, interesting.
If there was no atmosphere, on the moon, the sky would look black.
Even during the day?
Yep, even in the daytime.
Wow, so it's like having an atmosphere is what gives us that blue.
It really is, and it gets even cooler when you consider how the angle of the sun affects the intensity of the blue.
Okay, so what do you mean by that? How does the sun's position play a part?
Well, think about it. When the sun is high up in the sky around noon, the light doesn't have to travel as far through the atmosphere.
Yeah, makes sense. Shorter distance.
Right, so there's less scattering happening, but even though there's less scattering, overall blue light still scatters the most.
Because of that short wavelength.
Exactly. So that's why we tend to see the most vibrant blue sky at midday.
So the higher the sun, the bluer the sky. Does that mean things like pollution or humidity would also affect the color?
You gotta, those things definitely have an impact.
Because they change how much stuff is in the air, right?
Exactly. More particles mean more scattering, so sometimes the sky can look hazier or even a paler blue.
Wow. Never thought about it like that before. Okay, so we've talked about the midday sky, but what about sunsets?
Ah, yes, sunsets.
They're so colorful, all those oranges and reds.
And you know what? They're actually connected to the same scattering phenomenon we've been discussing.
Wait, really? How does that work?
Think about what happens as the sun starts to set. The sunlight has to travel through way more of the atmosphere to reach us because it's lower on the horizon.
Right, longer path equals more scattering.
Exactly. And that means even more of that blue light gets scattered away before it reaches our eyes.
So then what's left of those longer wavelengths?
You got it, the oranges and reds, they haven't scattered as much, so they become the dominant colors we see.
Oh, that's why sunsets are so vivid. It's like a whole different light show compared to the midday sky.
It really is. And this whole idea of scattering makes you wonder, what would the sky look like on other planets?
You're reading my mind. If our sky is blue because of our atmosphere, wouldn't other planets with different atmospheres have different colored skies?
Exactly. The possibilities are endless.
Could there be a planet out there with a green sky?
Absolutely. It all depends on what their atmosphere is made of.
So cool.
Yeah.
For example, what about Mars?
Mars has a much thinner atmosphere than Earth, and it's full of dust. This dust scatters those longer wavelengths more effectively.
So that's why we see those reddish-pink skies in pictures from Mars.
That's right. Each planet has its own unique sky signature based on how sunlight interacts with its atmosphere.
That's incredible.
Yeah.
Okay, but back to Earth for a second. We've talked about blue skies and sunset, but what about clouds?
Ah, yes, clouds, a crucial part of the picture.
They're definitely not blue. So what makes them look white or sometimes even gray?
Well, clouds are a bit different. They're not made up of those tiny particles like dust. They're made of much larger water droplets or ice crystals.
Okay, so much bigger stuff.
Yeah.
So what happens when sunlight hits those?
Because those droplets are so much larger, they don't scatter specific wavelengths like blue light. They scatter all the colors pretty equally.
Oh, so it's like all the colors are getting mixed back together again.
You got it. That's why we see clouds as white.
Okay, that makes sense. But wait, what about those dark storm clouds? They don't seem very white.
You're right. The thickness of a cloud matters. A lot. A thin cloud will let a lot of light through, so it looks bright white.
But a thick cloud with lots of water droplets wouldn't let much light through at all.
Exactly, and that's why they look darker gray or even almost black. Think about those thunderclouds.
Yeah, they practically block out the sun.
Exactly. They're full of water, ready to rain.
So the color of a cloud can tell us about what's going on inside it. That's pretty cool.
It is. Clouds are more complex than we realize.
They really are. This whole conversation has given me a new appreciation for something I see every day.
It's amazing what we can learn by just observing the world around us.
Yeah, so we've got those big fluffy clouds up there, but they're not blue like the sky around them.
Yeah, those water droplets are way bigger than those tiny particles we were talking about before.
So they don't scatter just the blue light.
Nope, they scatter all the colors of light pretty much equally.
Oh, so that's like they're mixing all of the colors back together, kind of like how we started with white sunlight?
You got it, and that's why clouds usually look white.
That makes sense. But wait, what about those really dark storm clouds? They don't look white at all.
Ah, good point. You're bringing up another important factor, the thickness of the cloud.
So like a thin, wispy cloud lets a lot of light through, so it looks bright white?
Exactly. And a really thick cloud with lots of water droplets packed in doesn't let much light through at all.
Which makes it look darker.
Yep, maybe even gray or almost black if it's really dense, like those thunderclouds.
Oh yeah, the ones that practically block out the sun.
Those are full of water just waiting to come down as rain.
So basically, the color of a cloud can tell us how much water is in it.
Exactly. Lighter clouds, less dense, darker clouds, lots of water.
Huh, that's pretty cool. I never realized there was so much to learn about clouds.
And that's just the tip of the iceberg. They play such a huge role in our planet's climate and weather patterns.
I know, right? It's amazing. It's like we take the sky for granted, but there's so much going on up there.
It's a constant reminder that there's always more to discover about the world around us.
Totally. This deep dive has been awesome. Thanks for explaining all this stuff to me and to everyone listening.
My pleasure, anytime. It's great to appreciate the beauty and the science of something as simple as the sky.
For sure. So next time you're outside, take a moment to really look up and think about everything we talked about today.
Yeah.
You might just see the sky in a whole new way.
And who knows, maybe you'll even start wondering about what the sky looks like on other planets.
Now that's a question for another deep dive. Thanks again for listening, everyone.